All right. So here we go. Looks like our last rocket attempt had some issues. Okay. Our pressure chamber burst. Overpressurized. Not good for our rocket. Okay. So clearly, we were doing some calculations pretty carefully to get the right pressure. We want to, hit the limit, just the right amount of pressure. But if you have too much pressure, then you have significant problems. Remember that this was our rocket that was based on baking soda and vinegar, mixing, reacting, and pressurizing the rocket, and then it would shoot off. The key thing we have to think about, and we have mentioned this before. Remember when we talked about the initial gas law stuff, and we said that there was this white solid that formed when when our rocket cooled down? That was the water vapor from the air, right? It was the ice, the solid that had formed. Well, that water vapor is present in our baking soda vinegar rocket too, because the vinegar is a solution of water and ethanoic acid, acetic acid. So clearly, we failed to take into account the water vapor. If you have liquid water in a situation, if you have liquid water in an environment, it will turn into a gas. It doesn't have to be boiling. You don't have to have a boiling pot of water. But if you have water in an environment, some fraction of the particles can turn into a gas and provide some additional gas in our pressure chamber. If we didn't take that into account, that would be something that could have caused us to have too much pressure in the rocket and would burst the pressure chamber that we're using for to contain the reaction until the pressure builds up. The key here is that we need to be able to think about what happens when I have multiple gases in the same container. What we want to think about is, okay, here is, a gas that's moving inside its container. These gases have some particular pressure. Now, if in addition to this gas, let's say this was our nitrogen gas or our carbon dioxide, if there was also some water vapor in the container too, I now have more particles. More particles mean more reactions, more collisions with the sides of the container, okay? Which means additional pressure. Mathematically, it turns out to be very easy to deal with all these additional particles bouncing around inside the container, okay? I add the pressures for the two different gases together. In other words, each gas behaves in the container as if it's there all by itself. And the total pressure in the container is the sum of the two pressures. So I can calculate the pressure of the carbon dioxide by knowing the volume, the temperature, and the moles of carbon dioxide. And I can calculate the pressure of the water vapor by knowing the volume, the temperature, and the moles of water vapor. And then I could just add those two pressures together. Each gas behaves in this container as if it is all by itself. We are assuming that the two gases don't interact with each other. That it doesn't matter that there are two different kinds of gas. All that really matters is the total moles of gas particles. I could add the moles of carbon dioxide plus the moles of water and do the total number of moles in a PV equals nRT equation and get P total as well, and should get the same answer. So what we want to do if we want to launch our rocket is we need to take the water vapor into account. We need to say, I know I want a total pressure of 5.25 atmospheres, okay? Or that's the atmospheres, that's the pressure of the carbon dioxide that I was generating, because I had assumed that that was it altogether. So I have to add the pressure of the water. Okay, the vinegar, the water in the vinegar, some small amount of that water turned into a vapor, turned into a gas due to evaporation, the process of a liquid turning into a gas below its boiling point, which we'll learn more about later. So I need to know what that value is so I can properly calculate the total pressure. Now, the way that we can do that, the easiest way to do that is to look it up in a data table. Okay? This is an example of a water vapor pressure table. This gives you the vapor pressure, in other words, how much pressure will the gas formed from the liquid water, what will it generate, when will it be at equilibrium, what will be its maximum pressure, based on the temperature of the water. So you can see as the temperature increases, the vapor pressure increases. And at some point, the vapor pressure will actually hit or equal the atmospheric pressure. That's what we call boiling. We'll talk more about that later when we come back from winter break. So we can look up and we can say, okay, we were at 50 degrees Celsius, let's say. So we go on to the chart and we say 50 degrees Celsius, the pressure of the water was 92.5 millimeters of mercury. So now I know that the real total pressure inside here, okay, was the sum of those two values, or 5.37 atmospheres of pressure. The 0.12, remember I converted the millimeters of mercury into atmospheres by dividing by 760. So that was my 92.5 divided by 760. That gives me the 0.12. So when you are collecting a gas over water, your apparatus involves the use of water. You have to take into account the pressure from the water vapor itself. Yeah, there are equations that you could use to do it as well, but that's not what we do in this class. In this class, we simply need to look it up on a table, or it can be just straight up given to you in the problem.
I'm confused. What if the amount of H goes negligible? Like, what if it doesn't matter, and you have 5 moles of CO2 and then 0.25 moles of H2O, but yet...
Well, 5 and 0.25 is not negligible, but yeah, you could have such a small amount, then you wouldn't need to worry about it. I mean, that's what negligible means. I don't
understand why the pressure that...
So it depends on the question that we're being asked, right? In terms of, is the water vapor pressure important or not? If my question was, what's the total pressure in the container, and you answered 5.25, well, that's not right. The total pressure is 5.37. Okay. Right? I mean, it just depends on the question. If I asked you how many moles of carbon dioxide were produced, and you used 5.37, as you're to calculate it, instead of 5.25, your answer is going to be off. And, depending on what this value is going to be off significantly. So yeah, sometimes you could imagine a situation where the pressure of the water vapor doesn't matter. This is not insignificant. I mean, 0.12 that's out of the whole thing. That's pretty important. That could be enough to cause it to burst or not. Right? At some point we hit that breaking point on the pressure chamber. All right? So that's pretty much it. This is what we call Dalton's law of partial pressures. And it simply says if you have multiple gases inside a same container, treat each gas as if it's in there all by itself. And if you want the total pressure, you just add the pressure of each gas together. Just add them together. Most common, we see these with water, because a lot of times we collect gases using a process known as water displacement. Okay? And this is where, if you've ever played in the bathtub, remember where we had the example where we were playing in the bathtub? Remember where I did this thing? And I can show this to you real quick. So you'll remember back when we started this unit, in the dim history of 4 days ago, we did this example where we had a container. We were talking about barometers and manometers, and I did this demonstration where I took this sealed glass container and I put it upside down in the water. I got a bubble in there, but that's not a big deal. All right, so one way, a very common way for us to collect gases is to take a setup like this and generate the gas in such a way that we can bubble it into this container. Okay? Let me turn the lights on for a second. We are going to do a lab where we do this next week. Do we have, what am I looking for? Yeah. So, we could set up a device where we have a chemical reaction that's generating a gas, like in a sealed beaker or something like that. And what we're going to do is we're going to take this and have it go through a tube. And so I'm going to slide this tube under, okay.
Is that your wedding ring?
This is my wedding ring. Left hands. Wedding ring's going. It's my class ring. From Cal. Not my high school class ring. I know. So, let's say you had, some sort of machine that generated lots of hot air. Okay? So we are collecting the gas. What gases are we collecting, right? Carbon dioxide, water. What's the main gas in here? Nitrogen. Remember, the atmosphere that you breathe in and out is 78% nitrogen. So most of the gas in there right now is nitrogen. There's actually going to be a significant amount of oxygen in there as well. Your body only absorbs a small percent of the oxygen you breathe in or out. Okay? So there's another gas in here that's also in the atmosphere, but even if I pumped in some gas that had no water vapor at all, the fact that it's bubbling through the water, that it's sitting on top of this surface of this water, means that some of the water here is going to evaporate, and I'm going to have water vapor inside this container. And so if I were to do any calculations with all this stuff, I'd need to take the pressure of that water vapor into account. This is called the water displacement method for collecting gases. It's the most common way at this level that we collect gases and work with them. And we're going to do a lab where you have to do that next week. You usually, not a thermometer, thermometers measure temperature, but we put the thermometer in the water. We measure the temperature of the water, and that, with the chart, would let us figure out what the pressure of the water vapor was. So, for instance, we could react, remember we're doing our baking soda and vinegar, okay? To safely launch the rocket, we need to get a total pressure of 5.25 atmospheres at 50 degrees Celsius in 10-liter pressure chamber. What mass of baking soda would be needed to react with excess vinegar to generate the correct pressure? We've answered this question. You guys have done this exact question before. The difference now is that we know that there's some water vapor involved in this process. We want a total pressure of 5.25. What pressure of carbon dioxide do we want in order to get a total pressure of 5.25? What do we have to take into account? We got to subtract out the pressure of the water vapor. So do that. Calculate the pressure of the water vapor. Which shouldn't be hard. I already did it. We did it in an example last screen. What mass of baking soda would be needed? So remember, the first step here, you want to take the total pressure, subtract out the pressure of the water vapor. That'll give you the pressure of the carbon dioxide. Once you know the pressure of the carbon dioxide, you can turn that into moles. What equation would I use to convert pressure into moles? Perv nerd, PV equals nRT. Here's my V, here's my T, convert to kelvins. I'm going to solve for moles. Find the moles of carbon dioxide. All right, so we have the pressure of carbon dioxide. We need to use PV equals nRT. Pressure, volume, R and T, we're trying to find for moles. So we can go ahead and solve. We get the moles of carbon dioxide, 1.93 moles of carbon dioxide. Now, if you look at the balanced chemical equation, the moles of carbon dioxide are the same. It's a 1-to-1 ratio. Moles of carbon dioxide to moles of baking soda. Okay? So we can go ahead and convert the moles of carbon dioxide into moles of baking soda. 1.93 moles of carbon dioxide, 1-to-1 ratio. That comes from the balanced chemical equation. We did it on Friday. The vinegar plus baking soda to produce carbon dioxide, water, and sodium acetate. So if you check the notes from Friday, it's there. Then we have to convert the moles of baking soda into grams. And you should get 162, 163, depending on a little bit on how you round it. Okay? Yay, we did it. We're great. All right, here's your reward. Baking soda vinegar rocket. All right, one more time. Baking soda vinegar rocket. All right.